Hello, everyone. We're on the air one more time. A little late today, but we'll make it. Yesterday we covered gluons, and just to do a brief recap here, remember we had gluons that don't look like particles anymore. They look like springs, and that's the way they portray them at CERN. CERN is the place over there, the accelerator over there in Geneva, Switzerland. And you can see that they're holding the quarks together with these bed springs, with which they represent the gluons. And I got a problem with that because there's no such notion as a gluon as a spring in the standard model. If you go to a standard model, they only talk about particles. And this guy is not a particle. This guy is supposedly some kind of bed spring. And that's what they portray there. They're not the only ones. Here's the Jefferson Labs one, just in case. That's in the U.S. And you can see that the gluons can't fly away because they're tied by these bed springs.
I mean, the quarks can't fly.
The quarks can't fly away because they're tied by these gluon bed springs that hold them together. You can see that they're kind of bound. And that's the image they want to give you. But what does that have to do with quantum? That's the question.
It's like a hula girl or those bobbleheads. You know the bobbleheads?
No.
Which is like a little souvenir toy.
Oh yeah.
Yeah.
And
that's kind of what this reminds
yeah,
me
yeah.
of.
It's
the spring with the ball at the end.
Yeah, and so the question is, what does this have to do with quantum, the bed spring? Okay, the mechanism we can all understand. The quarks can't fly away because they're held together by bed springs. Everybody can deal with that. Either this image or the previous image, which is this one here, right? Either one we can deal with. In other words, as far as the mechanism is concerned, we all understand it just by looking. We don't need any further explanation. The only issue here is, what does that spring, that bed spring, have to do with quantum mechanics, a particle theory? Okay, so this is cheating. This is lying. This is showing a mechanism that quantum cannot explain. They cannot explain how particles bring together two particles such as the quarks, and so they replace it for your visualization with a bed spring. Okay, and where do they get this idea? They get the idea, and it's kind of turned around, so keep that in mind. They get the idea from the fact that to pull a quark out of that triad, out of that system, you need more and more energy. So since the farther away the quark is from the other two, the more energy you need to pull it that far, they turn that around. They say, oh, see, if we drew a graph, we can show that force increases, or the energy necessary to pull it apart increases as a function of distance.
That sounds like a bed spring.
Of course, and that's
to pull it.
And right, and that's how they turn it around and turn it into the notion of a gluon being a bed spring. And again, that's where they get the notion. That's why. That's the reason why. And here you see, here's the French version, which I wasn't able to show completely yesterday, but you can see what's happening here. The fingers are trying to pull one of the quarks apart, and the farther it pulls the quark, the stronger is the force or the strength that you have to use, and at some point it breaks. And the issue is, when it breaks, it creates another quark. So not only do we have the issue of bed spring and elasticity, but we also have the issue where we're creating matter from the void. See, a new quark is created there. These U up is the up quark, and so they're creating a new quark over there. Okay, so that's their version. And this contrasts with the particle version, which is this one here, and this comes from the SLAC, Stanford Linear Accelerator, where they show that the quarks change color, which is another property, not necessary to mention right now, but the quarks change color because a gluon is pitched from one to the other. So a quark throws a gluon to another quark and changes its color. So you don't see any bed springs in there. All you see is that the standard particle model of quantum. You see that one quark is throwing a particle at another quark, That's the way it should be. I mean, if we're going to be consistent with quantum mechanics. So there's no place for, for this bed spring notion. And just in case, one more. Here we have another version. This is from the Science Show, and it shows that the quarks throw one particle at each other. And that particle is the gluon. It's the force carrier, the carrier of the strong force. And supposedly it is that mechanism that you're seeing there that keeps the quarks together. And of course, no one can imagine that, and that's why they had to bring in the springs. Okay, I hope that's clear. Here's another image just in case of two quarks falling apart, pulling and stretching the gluon in this case, and creating new quarks. So again, what does any of this have to do with science? What does this have to do with even what quantum proposes as a starting point, which is particles? None of this is related to either science or quantum mechanics.
Wait, real quick, are these observations that they made, or what are they trying to give a physical explanation? Physical interpretation of what observations are they trying to give?
They're just trying to say that you need more and more energy to pull two quarks apart. And since you need more and more energy to pull two quarks apart, they represent that the mediator between quarks, which is the gluon, they represent it with an elastic type of medium. In other words, it's either a bed spring, it's either a rubber band or a glue or bubble gum.
But did they see quarks
No.
to pull them apart? What's going on?
I'll get to that in a second.
Stop it when they get to that in a second.
Yeah, we'll get to that in a second. No, we'll get to that in a second. It's the question is whether they see. The answer is no. That's the quick answer. Okay. Here you have another version, and that's the bubblegum version. They stretch, the two gluons, the two quarks apart, and that's the gluon that's breaking and creating two new quarks. Okay, so that's what we have out there.
There's the gummy worm. That's
the gummy worm. Here's the rubber band. Okay, here's a different version. They're all rubber band, bubble gum, and bed springs. That's how they represent that mechanism, and the mechanism is related to the amount of energy you need to pull them apart. And and so the question is, what are they pulling apart? Well, they're pulling apart quarks. That blue one there and that red one, the color ones, those are quarks. Okay, and it takes 3 quarks to make a proton, and it takes 3 quarks also to make a neutron. Okay, they're qualitatively different, but it takes 3 quarks to make them. And where did we get this? Well, we got to start way at the beginning with Mr. Niels Bohr, and he wrote a paper in 1936 answering Einstein, Podolsky, and Rosen, EPR. And he's saying, he was being criticized that, quantum did not really provide a complete theory or explanation or description of how the world works. And so Bohr went out there and answered them with this paper. And I just want you to look at the title. The title says, quantum mechanical description, physical reality to be complete. In other words, the important word there is complete. He was saying, essentially, Bohr was saying that, quantum mechanics is a complete theory. Well, he was wrong. He died, I think, in 1962.
Well, he posed it as a question.
Well, no, you'll see it in his paper. If you read the paper, he says it is because he's answering them. Einstein criticized it's not a complete theory, and so he labels his paper, he titles it, "Is it a complete theory?" And in the paper he says it is. Okay, so if you read the paper, you'll find it's not so long, it's like a 5-page long paper. But he wrote this paper, he published it, and he says, yes, it is a complete theory. And but he was wrong, as all mathematicians are. And what was it, 1964, they created the quarks. Murray Gell-Mann and who was the other, Swiggy? They came up with the notion of quark. 3 quarks for master mark, I think was the phrase they got out of a book, and that's what they used, the word quark, to label these. And those are the quarks there. Again, as you can see, they're interconnected by this springy thing, supposedly a bed spring. And what's interesting that you see there, it says, this is not, where is it? I think it's the next one down. That this is not the exact representation or physical form that a quark has. Okay, I think it's there in the next one there. Yeah, there's often down quark. Oh, there it is. Note: quarks don't actually look like this. Yeah, they don't look like that. So why did you put that in there if they don't look like that? And do gluons look like that? Well, I guess they don't look like that either. So what is this a representation of? What are they illustrating there if neither the quarks nor the gluons represent, what they think quarks and gluons look like or are in reality? So what is this nonsense? What is this illustration for? And again, a lot of this is just to show you that from a physical perspective that, the quarks don't run away because they have this bed spring tied to them. And what they're really trying to say is you need more energy to pull them apart the farther the distance. And so they represent that with that bed spring. That's the way it works. Okay, so what is a quark? Well, let's look at it. Here's a definition of a quark. Quark is a type of elementary particle and a fundamental constituent of matter. No kidding. Okay, fine. Quarks combine to form composite particles called hadrons, the most stable of which are protons and neutrons, okay? So they don't break apart. We don't know why. We think it's because they're made of 3 quarks which are bound by bed springs. Okay, fine. That might explain that. The components of atomic nuclei. Due to a phenomenon known as color confinement, quarks are never directly observed. That's the part I wanted to show. They're never observed. We've never seen a quark, okay? We've never seen a gluon, which is smaller, or found in isolation. They can be found only within hadrons, which exist as either baryons, which include protons and neutrons, or as mesons. For this reason, much of what is known about quarks has been drawn from observations of hadrons, which they can't see either, by the way, because they don't observe. They use the word observe, but they have never seen a hadron either. They haven't seen an atom, and a hadron is part of an atom.
What did they observe? Where did they get all this
what they're
Where
doing?
Did we start with?
They don't have any observations whatsoever. They've never seen an atom, much less anything subatomic.
Well, then how do they know it takes more energy to pull?
And again, the way this works,
they're just using more electricity to do something.
Yeah.
But,
exactly.
But how do they know that they're pulling things apart even?
Okay, here's the answer. Now I can answer your question because right on time with that question. Here's one paper, not the only paper, but there's several papers on this, but here's one paper and tells you why. Okay? And the paper is titled, Measurement of the Top Quark, blah, blah, blah. It continues. The title is written by a German there. And essentially what they're saying is, let's see if I can read it there. Make this a little bigger. It's too small for me there. The top quark plays a special role in the standard model of particle physics with its enormous mass of about 170 giga electron volts, GeV. It is as heavy as a gold atom. And I don't want you to read any of the rest because that's where we can put a period and stop right there. She's saying that the top quark is as heavy as an entire gold atom, which contains protons, which contains inside it a top quark. Do we have that right? We have an atom. We have a gold atom, right? Gold atom has...
They didn't say what atom.
No, it's a gold atom. Yeah, a gold atom. It says, as a gold atom, it says.
As heavy as a gold atom, but they didn't say how, like what part of what atom is this quark?
Of any atom. Any atom. Top quark is a component of the proton.
Oh, okay.
So we have three quarks make up a proton and also a neutron. But let's just talk about protons to make it simple. So we have 3 quarks make up 1 proton. Many protons make up an atom. Many hydrogen atoms make up a gold atom. And the top quark weighs more than the entire gold atom.
As much as the gold atom.
Yeah. Now, does that make any sense? Here's an illustration of it, just so you...
To make that clear, a part of the gold atom weighs as much as the gold atom.
And here's
which is to say that everything else weighs nothing. The whole weight of the gold atom is in the top quark, is what they're saying.
No, they're saying something because it applies to any atom, even to uranium atoms. That means that if you take a top quark from any atom,
even the hydrogen atom,
correct,
then the hydrogen atom should weigh as much as the gold atom.
No, they're saying in reverse. They're saying that the top quark weighs almost as much as a gold atom, and if you take the top quark of a hydrogen atom, the top quark weighs more than a hydrogen atom.
But that's what I'm saying. The hydrogen atom should weigh at least as much as a gold atom if it has a top quark.
And they say it in reverse. They say the top quark simply weighs more than the hydrogen atom.
Yeah, but if you follow that logic, then the hydrogen atom everything should weigh as much as a gold atom because they all have
or more.
Or more.
Yeah, and here you have the representation of that. We show that a seed of the apple weighs more than the entire apple to which it belongs. That's what they're saying.
Did she say can weigh as much as?
No, it is.
No, but the words that she used is can weigh as much as. So does it go up or down or what
she says that they're approximately equal.
No, but the language she uses can weigh as much as a gold atom. So sometimes it weighs this, sometimes it weighs that. Is that what she's saying?
I'm not sure what she's saying there, and I'm not concerned about that at all because of the following. Let's get the crucial issue. We're still not on the crucial issue. The crucial issue is the seed weighs more than the apple. That's what they're saying.
We got that.
I'm not sure that's clear. We're saying the seed weighs more than the entire apple for any apple. If you take a pumpkin, the seed weighs more than the pumpkin. If you take whatever fruit out there, the seed weighs more than the apple that contains it. That's what they're saying.
We got that.
And that's all we want to concentrate. We don't care about any of the other detail. Is that irrational right there and then? Can we stop there and analyze that? Can we say, look, is this irrational? Is this the greatest nonsense that ever was invented by man, that the seed can weigh more than the apple that contains the seed? And here we have a serious problem. That's what we have to concentrate on and not get into the nitty-gritty. If the seed weighs more than the apple, we have a serious problem here. Where did they get this nonsense? The nonsense comes from trying to accelerate the amount of energy. Again, they get into this energy deal where you need more energy to accelerate a seed than you need to accelerate the apple. That's essentially what they're saying.
But then again, back to the observation thing, how do they know that they're accelerating the seed at all?
This is the issue. They've never seen a seed. They've never seen the apple. They've never seen the apple, let alone the seed.
You don't have to see it. You can make it see. Understand the derivative of what you're doing. But what did they actually do? What are they putting energy into?
They don't know. They don't have the slightest clue.
Well, I don't care what they know. What did they do?
What they did was they created some species. It's called species. They created some atoms, some molecules. From a canister, maybe a gas canister. I can only relate to what I did because that's essentially what we did. We took stuff like phosphine and we extracted from there the phosphorus and we ionized it. Supposedly we removed an electron, so now we could manipulate it with magnets. And now we accelerated this ion, right? And we accelerated the ion through the beamline.
Okay,
until
everything you said so far is derivative. You haven't seen anything of what you're doing.
Oh,
you're
correct.
doing a whole bunch of invisible stuff, but you can understand at least, placeholders of everything you're doing.
Right.
That's why I want to know what did they do, and then explain in an illogical way. That's my point.
And again, they've never seen an atom.
But what did they do?
Well, what they do is they create a plasma. What is called a plasma. In other words, they ionize a gas. They can see the gas in there. They pour the liquid first before starting. They pour the liquid in a canister. So they have, for example, phosphine in there or some other chemical. It doesn't matter. But they can see the chemical. Okay, they can see the water or the gas or whatever they're pouring in there. That part, up to that point, the eyesight is useful. And that's where the eyesight stops. At that point, they just ionize it. They say, okay, let's put some electricity in there. Let's ionize the gas. So they ionize the gas. That means they're going to remove an electron from it. But this, but now they're just conceptualizing. Now they're not seeing what they're happening
gas
in there.
in there, and then they put electricity.
Correct.
The gas.
And now they're going to remove an electron from the atom. Okay, supposedly that's what they think they're doing. Not that they've seen it, but this is what they think they're doing.
Let's put them in parallel. What they're actually doing and what they think they're doing.
Okay,
right?
good.
In parallel, they got a gas canister and they're throwing electricity through it.
Okay.
Yeah,
they're ionizing the gas.
And what they think they're doing is they're ionizing the gas.
They think they're removing an electron ball or bead from the. So that's the explanation. They've never seen that. That's the explanation they give to what they think they're doing in the gas canister.
And where's the quark coming?
Okay. So now the issue is that now they're going to accelerate this ion. In other words, they're going to get the atom itself.
Just
the gold atom.
Just one atom
they
of
think,
the gas.
They think.
Okay, what do they actually do?
Well, if you go under the rope model,
No. I mean,
okay,
what are
that's
they actually doing with the can? With the gas can?
Well, not the gas can. They're just letting this the gas, the ionized atoms, the ionized portion of it go through a tube.
Okay, so
and
put
go
a
into
tube the can. I want to know the macro stuff.
Oh, okay.
They put a tube into a can and let the electric gas go through.
Yeah, hold on. Let me put ourselves back in. We're talking here in the dark.
With the seed in the apple.
Yeah, we left them with a seed in the apple. Is it here? Okay. Okay, so what it is, we have a gas canister. Yeah. Let's go slowly. Yeah, you're right. In a way, we got to look at this. We have a gas canister. We ionize the gas in there, okay? And we pull atoms, or they think they. So one thing is what we're doing with the can. We can see the gas. We can see the liquid. Whatever we put in the can, we can see. That part is macro.
We can see the tube.
That part is macro. That part we can see. We can say we observed. Okay, well, now
we did observe.
Now we did observe. We can talk about observing the gas inside the can, or observing the liquid if sometimes it's in liquid form. Okay, so now they're going to ionize that. They're going to supposedly. Now this is the explanation. This is not what they see. This is their physical interpretation of what they think they're doing. They're saying you have an atom, and the atom is a planetary atom, right? Under quantum.
Should we go through the physical macro, the whole movie first?
Okay.
We have a can, we have gas.
Okay, so now a gas goes into the system. Okay, goes through a tube.
Gas.
It's ionized gas. Okay, we'll call it ionized gas. That's all we can say.
But they threw electricity through there to ionize it, right?
Yeah, supposedly they removed an electron bead from the atom. Okay, that's what they think they're doing. Okay, now they send this species into a tube and they send it into the beamline. The beamline is going to carry this all the way to your target. Okay.
What's a beamline?
Beamline is a series of magnets all around a tube. So there's a tube and it's surrounded by magnets.
Okay, so the tube is parallel with this ring of magnets.
You have a ring of magnets around the tube. Okay. And the ring of magnets you can manipulate. In other words, you can increase the magnetic attraction of each magnet. You can control that. Okay, so if you need to squeeze the beam into a pencil point, you can do that. You can squeeze the beam and you can make it wider. You can manipulate
within the tube.
Within the tube, you can do that by just adjusting the magnet power.
Basically,
okay?
you can adjust exactly how many atoms are going through at each second. You can make it all the way down to so it's one atom. It's a line of atoms, basically.
They think.
Okay. No, but
it's important to say that they think they're doing that because the rope model has a different version of that same thing.
All we're doing is we have magnetism.
And we're compressed, and we can manipulate the species because the species is ionized. Okay. And again, under quantum ionization means that we removed an electron bead.
It's like the oil drop experiment where they ionize it just so that they can manipulate it with magnets.
Correct. Okay. That's exactly the same thing. And so the issue here...
Wait. Well, that's it?
No, hold it. Let's go through the whole macro process. So what happens? You accelerate the ion, okay? Just pick one, and we'll call it, in this case, the gold atom turned into a gold ion. Okay, so we have one atom of gold, and we remove one electron from that whole monster, and we're accelerating just one atom. That's what we think we're doing. Okay, so far.
With magnets,
we can manipulate it with magnets.
The speed of it.
Correct. We accelerate this thing around the beamline, and we'll say that it's like a torus. It's circular. Okay, so now we accelerate this gold atom. It's really a gold ion. Okay, it's going around, and now we have another gold atom. We send it in the other direction. Okay, so we have one going this way. We'll call it clockwise, the other one counterclockwise. Okay, viewed from the sky, that's what it is. One clockwise, the other one counterclockwise. Okay, so we got them going around like that. We accelerate them. We can, with the magnets, we can make them go faster and faster and faster. And we need so much energy to make that happen. Okay, so
that's the crucial part.
Yeah, we have this energy control. How many giga electron volts? I only work with kilo electron volts. Where I worked, but giga is just a billion. I work with thousands of electron volts. These guys work with billions. Okay, fine. So they need more energy, and it's important to keep that in mind. Giga electron volts, or whatever EV, electron volts, stands for energy. That's the amount of energy you need to accelerate a particle. You increase the energy, whichever way you do that, right? Maybe introducing spirits in there, whatever you do, I don't care, but by increasing the energy, the electron volts, you're increasing the energy, okay? So now this thing is going around one direction, the other one's going out in the other direction. Here you have the chamber, and in there you put the two beams so that they match, they hit each other, okay? That's what they think they're doing. Again, we haven't seen this. All we know is this is the explanation they give.
That's important to say at every step.
Yeah.
Because sometimes we'll think, we know what's going on.
No, they have never seen any of this.
Really, they're not even looking at, you can't even see magnetism. So all you have is just...
All we ever seen is the gas canister.
Yeah, that's crazy.
We can say the word observe up to that point. Then the eyes stop. We become blind, and now we use the mind.
We have a tube.
We have a beamline. We don't know what's going on inside the beamline. We have a chamber. We don't know what's going on inside the chamber.
You don't see the atom coming out. You don't see the magnetism.
Right. It's all interpretation.
Yeah, you don't see anything is coming. Okay, the gas canister is open, so something's coming out of it.
Oh no, no doubt there.
But you don't know how much of what it looks like is coming out of that gas canister.
It's all interpretation
into this tube, and it's all invisible. And the magnetism with which you're accelerating it is invisible, and the energy that you use to power those magnets is also invisible.
Correct. You got it right. The only part that is observable is the gas canister,
the tube, the magnets.
The physical magnet, not the magnetism.
The magnets.
Right.
You see the magnet. You see the plates. You see the tube. You see the gas canister, and the gas canister is open. It's like a crime scene, but everything else is invisible. And from then on, you gotta. There was a game a really fun game that I played with my brothers where you get like the initial scene.
Yeah.
Or not the
and you got to figure it out like Clue, Clue.
Yeah, it's kind of like Clue, where you get to ask any questions
to try to figure it out.
And however long it takes you to find out what actually happened, that's essentially your score. And that's kind of what this is. All you have are magnetic plates in a torus shape,
and you got
around a tube connected to an open gas canister with some liquid in there.
And that's it. That's all you can see.
That's all you can see.
And touch, for that matter. I mean, I've dealt with these canisters, and you put them next to a machine. We called them implanters. We implant species into the wafers in the semiconductor industry. And again, I worked only with kilo electron volts, but the mechanism is the same, exactly the same. It's a create a species, accelerate it through the beamline, and shoot it at a target. That's exactly what these people are doing, except that they're doing with giga electron volts, higher energy, and they're looking at stuff that they can. Well, we couldn't see our stuff either. We couldn't see ions. They're talking about electrons and accelerating. I don't think they talk about accelerating photons. Maybe they do, but they do talk about accelerating electrons. And we dealt with ions, which is much bigger than an electron, supposedly.
Okay, hold on. There's one more step to this, to the macro thing. What they see is they know that they can line up two some things to hit, and they know the moment it hits and where it hits.
Something hits, something touches. That's no doubt. Yeah. That's going to happen inside the chamber.
but they know when and where.
Yeah, because you have the beams, you align the beams, and all that's controlled, right?
Yeah, but align the beams as invisible things.
Yeah, correct.
But
you don't know what's coming out of those.
They're aligning two somethings. They know that they can manipulate the
two
invisible.
Somethings.
They can manipulate the invisible to a certain degree.
Correct.
Essentially to a perfect degree, so that they know when and where these two somethings going in opposite directions, if they are going in opposite directions, touch each other. And they see some fireworks, or they have a machine that detects
that and analyzes it for them.
But it doesn't analyze it. It gets some sort of feedback. We can say it as vague as possible. It gets some feedback from the when and where that it crashes. Right? So it's not like it's completely invisible. We kind of get some
but
shadows.
Keep in mind something. You can also manipulate iron filings with a magnet. Now that you know that a magnet attracts iron filings. Right? Once you establish that, you can say, okay, then if I get near enough to an iron filing, I can pull it over with the right amount of magnetism. Mm-hmm. So you are able to manipulate this thing that you can all see it. It's all in front of you. It's all macro stuff. Yeah. So you can say, okay, so I can do something with this. Maybe I can make this iron filing crash against this other iron filing, since I know how much magnetism I need, how many Gauss and whatever, to manipulate this thing, so I can make them crash. And that part we have no problem.
That's the interesting thing. We can measure all the invisible things.
We can measure right.
We can get descriptions of the effects of the invisible things, and with those descriptions, we can do a lot of magic tricks, essentially.
Exactly. In other words, you don't have to see magnetism in order to use it, which is what these people are doing.
Which is worse, because you don't even have to know how it works to be able to use it, which is what we said.
Right. Of course, because if you simulate it with particles and Mother Nature doesn't use particles, well, yeah, you're going to be able to simulate it and say, okay, I can do this with particles. Okay, fine. Especially in the case of acceleration and clashing, smashing two particles, you can do it all with particles, and everybody can relate to that. That doesn't mean that's how Mother Nature's doing it. Maybe Mother Nature's doing something else.
Okay, so we got the macro. What do they think they're doing now? Let's get let's put the next folio.
And we're missing a part, and that's where they touch. But we'll get to that in a second as well, because that's important too. How they get to the quark level.
Yeah, I wanted to get to that.
Okay, so we're getting there.
What do you want to go on to? What do they think they're doing?
Yeah, very briefly. But what there's to think they're doing is, at least from the canister, first in the canister.
Yeah, let's go step by step.
Inside the canister, they believe that you have the planetary atom, and they deny it, but they constantly use the planetary atom. That's how they explain these things. They say, look, you got the planetary atom, you have the bead going around, the electron bead, and we're going to remove the bead from it.
You got a whole bunch of marbles in this can.
Right. Well, you have. It's important to know that you got the little marble going around the bowling ball. That's the image.
That's why it's called planetary. Okay.
Yeah, so now we're going to remove the bead, and now the bowling ball is positively charged, whatever that means. Yeah, and now we can manipulate it with magnets.
Yeah, it's ready for magnetizing.
Right. Now, whatever we did to it, we just removed an negative electron charge, whatever charge is. And now the other guy is positively charged, and we can manipulate it with negative magnetism.
We removed the moon from the sun and not, from the earth. We removed the moon from the earth, and now the earth can be moved by magnets.
Yeah, we can move the earth by magnets, by the negative magnets, because the earth is charged positively. Okay, so that's it. So now
that's not it. So you have these negative somethings.
Correct.
Sorry, positive something.
Yeah, positive ions. Yeah,
marbles.
Yeah.
Now it isn't
bowling balls.
Okay. Ooh. Bowling
yeah,
balls.
these are big monsters.
You took the marbles away.
Yeah, I took the marbles out.
So,
the negative marbles.
So you let the bowling balls, because now it isn't planetary. Now it's literally just balls.
Right. Right. It's the ball stripped of its electron.
Yeah. So now it's not even planetary. Now we literally are just dumping a whole bunch of very microscopic bowling balls.
You still have planetary, because remember, you're removing only one electron out of many that like gold has. Okay. So let's keep that in mind as well.
It still is planetary.
Yeah, it still is planetary.
So it's still a whole bunch of marbles going around bowling balls.
And you're accelerating this along the beam line.
So you roll them into, I guess, roll?
Slide or roll, I don't know which one. They never clarify if it's slide or roll.
They go into the tube. Let's make it nice and vague.
Yeah, they travel.
They think that they travel into the tube, right?
Yep.
Wait, but it's two tubes, because one's going in the other direction, right?
Correct. You're going to manipulate
Wait, two tubes or one tube?
It's two beam lines.
But in the same tube?
I'm not sure. I think they
'Cause
are.
they have to hit at some point, right?
I think they're in the same tube. They just have them like in parallel.
Yeah.
So one's going here, the other one there, and then they just meet the beams inside the chamber.
Okay, so let's just focus on one for now.
Okay.
So we have these bowling balls with little marbles rolling out, going into the
Beam line.
The beam line, the tube.
Yeah.
Which they consider the beam line, and
Yeah.
then with these magnets, I don't know how they explain magnetism.
They don't have to.
So they just know they have magnets that
Yeah,
push these.
no. But listen,
negatively charged.
this is easy also to understand. If you have a positive species, you removed an electron from a gold atom. Now it's positively charged. All you need is positive magnets to squish it together.
Negative magnets.
No, positive, because you
Oh,
couldn't.
true,
Yeah, you got to push it in. You
True,
got to
true,
squeeze it in. So you're going to squeeze all these atoms into a single pencil point kind of thing.
So they think that they have a row of atoms or just one?
They claim sometimes that they can accelerate a single electron, a single proton. Nonsense. Total nonsense.
Okay, but they think. Let's stick to what they think.
Correct.
So
that's what they think they're
so
doing.
you open the gas canister and only one rolls out?
Mm-hmm.
They're precise with that shit.
They claim they can't see it, they can't take a picture of it, but they know they're dealing with one.
They open and close it real fast to make sure only one rolls out.
The shutter goes up and down.
It's like a Pez dispenser. Okay, so one marble roll.
One marble, one bowling ball. One bowling ball with planetary bowling ball.
Let's say this precisely. One bowling ball.
Planetary bowling ball.
Yeah, one bowling ball with many marbles, but it's one less than it used to have.
Correct. Is
rolls out. Let's just say rolls out. Rolls
Okay.
out into the into the tube. Then they close the gas canister. Gas canister is closed.
Yeah.
They magnetize question mark whatever that is.
Yeah. They squish it with magnetism.
They make it a beam. So they push this
forward.
Bowling ball. I guess it's rolling or flying.
We don't know. It's
I guess it's flying because we're also
in this case they think it's flying. Yeah.
Okay, so it's flying.
But whether it's rolling inside that flying, I don't know.
Yeah, true. Because it's. I mean, you still have to.
Maybe it's just sliding, instead of rolling. But it could be rolling or sliding.
Well, at that point, you have to explain. They'd have to explain what magnetism is, so that we have a clear picture of what magnetism is actually doing to.
They'll never tell you if this thing is rotating, for example.
But that's the point. Until they explain exactly what they think magnetism is, that we can't really say for sure if the magnetism is making this bowling ball slide or roll or what.
Right.
Okay, but let's just say
or
it goes.
Spin, yeah, whatever.
We're just gonna go as vague as possible because that's what they do.
Yeah.
So they think they have this bowling ball that's going because this magnetism, and they have another bowling ball going in the opposite direction. They spin them, and then they basically focus it in with their precision with magnets.
Right.
Till both bowling balls crash.
Okay.
And now where does the quarks come in?
Okay, now at this point, you smash two gold atoms together. And now you look at the debris. You throw the hand grenade, you see the explosion.
Oh no, it's like shooting two bullets at each other.
Two bullets or you can conceptualize any way you want. You shoot two bullets at each other. Now you look at the debris that comes out of that from ground zero, right?
The shrapnel.
The shrapnel, right. And so now you try to image that. Now how do you do that? Do you see that? No, if you can't see an atom, much less can you see the debris from an atom. So what do? They look at all these squiggly lines that they are able to image. They say, okay, here was one particle, another one over here, another one here.
Let me stop you there because that's a very important part.
Yeah, it is.
Do they have a camera on the spot?
It's no camera. This is done by computers. This is not like you take a photograph.
No, not a photo, but
it's
but
imaged.
Some sort of How is it imaged?
It senses signals. If you can relate to that.
But the thing that is sensing the signals, is it above?
I'm not sure where it's located, but the point is that it's the algorithm behind it is already designed to treat every signal as a particle. It's already biased in the sense that...
But that can't be true exactly because as far as I understand it, they just need something that senses things, right?
Correct. A detector. Let's call it a detector.
But the detector just picks up signals.
Correct.
It doesn't interpret them yet.
But the algorithm does.
What algorithm? So we have a thing that picks up the signal and then it gets translated?
Correct. It gets translated and imaged based on that translation.
Why does it have to be translated?
Because you can't take a picture of it directly. In other words, it's got to have it senses something, some movement, some vibration, and says, what was that vibration? And the algorithm says, treat it as a particle. That's essentially what they're doing.
I still don't understand why it would need an algorithm.
Because how else are you going to translate signal into something that we can relate to? I mean, you're going to make a picture of this.
Yeah, you just image it. What
are you going to image?
Why can't you just image wherever it picked up signals? Without
but then what are you gonna put on? I want to know what I'm gonna put on the photograph. What am I gonna put on the picture?
Wherever it picked it up.
But not where. I need to know what, not where.
No, you need to know where.
Well, I want to know what.
First, we need to know. That's my point. You don't need an algorithm. You just have if I have a bed of sand, right?
Okay.
And I throw 3 invisible somethings, I don't need an algorithm to know where these invisible somethings landed.
But that's what they want to know is what it looks like. In other words, what they're looking for is particles. Remember that. Keep that in mind. They're saying we know that an atom is a particle, small particle, but it's still a particle made of little particles itself.
Okay,
and what we want to know from this smashing, what particles come out of there. So they have to turn them into particles.
Are you saying that they built the sensor, not the algorithm, but the sensor to only pick up dots kind of thing? Not lines?
I'm not sure exactly what the sensor picks up. I think it picks up signals.
Yeah, but
some vibration.
But that's a crucial part.
Yeah,
I know what the sensor actually picks up before you can criticize the algorithms that interprets what it picks up.
Well, the point is that whether you when you look at the whole system from detector or sensor all the way to where it's imaged, that whole system is built on the basis of particles.
Okay, so
there's an assumption, a pre-assumption that we're only going to deal with particles, so it's kind of it confirms quantum mechanics because you haven't challenged quantum mechanics by saying I'm going to treat everything as a particle.
It's called a self-fulfilling prophecy.
Yeah, it's a self-fulfilling prophecy.
Okay, but back to the quarks. So what do they see? What do they think they're seeing?
Okay, so now they smash 2 gold atoms, gold ions. What they think they're doing. Okay, they think they're hitting 2 atoms together, 2 lonely atoms. They hit them together, and they get this. Where is it? Here's the famous Brookhaven. Where is it? Here's the Brookhaven gluon and quark mess. Here's the collision of 2 atoms. And one of the things you want to keep in mind here when you look at that image
that is looking back at you.
Yeah, it looks like an eye. It looks but I want you to look at something in there very carefully. You'll see that it's almost perfectly symmetric. Mm-hmm. Now you look at all around.
That's not the right
word.
Symmetric
in the sense that it looks like every line on the right hand side is equal to the one on the left. The ones on the top, the north equal to the south, the east equal to. In other words, if you look, but all around it looks like it's. Perfectly symmetric from ground zero outwards. You could almost say, it's a perfectly symmetric ball made of lines. And remember, this is a cross section of a ball.
You always got to keep that in mind. That we're looking at a 2D cross section of a 3D happening.
Correct. That's. But see how symmetric, how perfect it is almost. Let me show you. Well, let me compare it. Let me compare it so that you see what I'm talking about. Here's a hand grenade explosion. Let me compare that to you so that you can see the difference. This is what debris would look like if you smashed 2 things together. And this is really a hand grenade explosion, but it just puts it in the proper context.
Isn't it the same thing?
Well, not really. You can see that look at the particles. They're flying all in different directions, at different speeds. One is bigger, the other one is smaller, right? So it's not perfectly symmetric. If you look at just the lines on the outside of that explosion and the debris, they're not all symmetric. They're different sizes of particles. They're different speeds, okay?
It's like a very it's like a grenade explosion with zillions of shrapnel, all the same size about.
Right, and here look at this.
Chunks, small chunks.
Right, and here you can see that the debris here is perfectly symmetric in comparison. Now,
not perfectly, because
well,
it's more symmetric than that. That's the best we can say. Let's not say perfectly symmetrical.
Okay,
if you see
but
one
it's
line,
okay. But you can see that this is very, very symmetric. Now, let me tell you something else about that picture. What you're staring at, supposedly, keep this in mind, you're looking at traces. So the particle is at the end of the road. On the outer perimeter. The particle is supposedly on the outer side, and what you're looking at is a picture of a movie.
Okay. I see
You're looking at a picture of them. All those lines are traces of particles.
Oh, it's like when the lights are off and you have like a glow stick.
Yeah.
You see the trace of the glow stick.
How do you put that on a picture now? See,
you
picture.
Can take pictures of traces.
Yeah, but that's
that
because the camera is able to look at each one of the points in there, right? This is an explosion that happens at such great speed that they have to have a camera that can, or a sensor that can detect every location where there's a vibration inside that chamber, and convert that into some kind of image. That's what they've done here.
That's the thing. It goes so fast that it looks like
and that's what they want to show. But the question is that what they're looking at, or are we looking at the ropes connecting to an atom?
Yeah, it could just be lines, right?
Right.
Like
it could be
ropes.
It could be connections, and what we're doing is vibrating the ropes, and somehow we are imaging the vibration of the ropes. I mean, we can just as well interpret it that way. That's all I'm saying.
Crazy if we're shaking all the ropes that make up the atom.
Right, and that's the point.
Whoa.
Look at how symmetric this thing is. What we're doing is shaking the spider's web here and taking a picture of the vibration of the spider's web. We're not looking at two particles colliding like a hand grenade would explode against another one. What we're looking at is the shaking of the spider web. Maybe. I mean, there is a different interpretation here.
But this would be a good way to count how many atoms there are in the universe. If you could count each one of these.
Oh yeah, but I don't think
if you could discern each and every
but I don't
line.
think you can see all the ropes coming
Obviously,
in.
No, that'd
I don't
be
think you can. I think we're getting a big picture of what an atom really looks like, and that is, what you're looking at is the proton inside the atom, and there's many protons in there in this atom because this is supposedly a gold atom. But you can see that the lines are extending perfectly symmetric out of that center point. This really looks a lot more like the rope hypothesis atom than it does two colliding hand grenades. The two colliding hand grenades would look, again, I think it would look more like this. If you really collided them, you would see something along these lines. You would see particles going everywhere, and you can see that the fire there, the glow is not perfectly symmetric. The particles are not perfectly symmetric. They're not all the same size. Why would all these particles be of the same size, essentially? Because you can see that if you look at all those lines, if those are traces, that pretty much suggests that all of them are more or less coming out of ground zero at the same speed, and they're all the same size.
Yeah,
why would that be the case?
That's the important part. They're all the same size. You don't see like one big atom or
right.
Gluon or Quark. Oh yeah, what we're
you would think
Quarks,
that one. Okay, yeah, and so what we're looking at. See, this is the problem. This is where we get to the quark level. You say, well, how many particles are in there? Look, can you count all those particles? I mean, there's gazillions of particles there, right?
I'm gonna say 15.
I mean,
that's
you can't.
My best guess.
I mean, you can't even count them, and that's only a cross section. Imagine this 3D. The count is astronomical. You're talking about millions or billions, right?
Trillions.
But see, the problem is that here's the problem. The problem is the gold atom has only 84 protons and neutrons.
So there's only so many.
So we should only see 84 lines there.
No. Times 3, because there's 3 quarks per.
Okay, so let's get into that. So now you can say, okay, no, 250 rounding off. We can get 250 particles out of there if we're talking about quarks. So what are all these lines?
The gluons, I knew it.
Right, and so now we have to get into the gluons, and we say, well, these are gluons. So here we have, hold it, let's get the sizes here right. We have the atom, which we can't see. The proton is a part of the atom, we can't see that. And here we're talking about a quark. There's 3 of them in each proton. and they're bombarded between themselves by countless gluons, which we can't see those because these are marbles compared to quarks. You know, you're talking about quarks being bowling balls here and marbles hitting them. And these people are saying that what you're staring at is a gluon quark soup. You're talking about gazillions of gluons, and they say they can image all these gluons in that picture.
Because we're back to what we were talking about yesterday, where you don't have to do the accounting for the gluons.
Correct.
You have to do accounting for the quarks, because there's only 3 quarks per
right.
proton and neutron.
And
but the
for
gluons,
protons you can also...
Yeah.
But
the
gluons, unlimited.
That's a bottomless
bag. Pit. Yeah. You've got a bottomless pit.
So whatever we can't count with quarks, we count with gluons.
Right, and this is the problem. The problem, and here, just let me put this in the right context here. Here is what atomic mass means. Atomic mass is the sum of the numbers of protons and neutrons in the atom. Electrons contribute so little mass that they aren't counted. Okay, so essentially atomic mass, what is atomic mass? Numbers of protons and neutrons. What is atomic weight? It's the weighted average because some atoms have more neutrons than protons. And so they take, and there are different isotopes, meaning isotope is a different type of atom of the same type of atom. In other words, it just has more neutrons or fewer, or usually more neutrons. In fact, I think in all cases it's got more neutrons than protons. And the point here is that atomic weight is just a weighted average of these different types of atoms, and their and how many of these are in nature.
So we have many gold atoms. Each one weighs about this much, or you take the average of all the ones we've seen, or a select group. So this gold atom weighs more than that gold atom, but we're just going to take the average.
Right, but here's the crucial point that I want you to keep in mind. Let's go back to the apple and the seed. Seed weighs more than the apple. Okay, here we have the seed. It weighs more than the apple. The apple is the atom, and the seed is the top quark. The top quark is part of a seed, actually a smaller part of the seed, which is a smaller part of the apple. But these people are saying that the top quark weighs more than, for example, a hydrogen atom, because the top quark weighs almost as much as a gold atom, or thereabouts. So if you take carbon, and it has several top quarks in it, each top quark weighs more, or has more mass, to be more accurate, more mass than the carbon atom. And you say, how can that possibly be? And now we can answer that question, how they're doing this. If the definition of atomic mass is the sum of protons and neutrons inside an atom, we can all understand that, right? So you just count the number of protons, the number of neutrons, that's the atomic mass of a given atom, right? But now the top quark is part of that proton and part of that neutron. How can it weigh or have more mass than the atom that contains it? Well, again, what they do is they're talking about two different things. They're talking about math, and they're not talking about physics. When they're referring to atomic mass, they say count the number of objects inside an atom. So we count them, we come up with atomic mass. It's the quantity of matter. But when they're talking about the top quark and having more mass than, or just as much mass as a gold atom, they're talking about something else. They're saying, look, if you try to accelerate this thing, you're going to need so much energy. And what is energy? It's another form of mass. So now they're no longer talking about the quantity of matter. They're talking about the amount of energy necessary to accelerate it.
That's where this linguistic tricks comes
Correct.
back into play, where you think we're just talking about semantics, but it's like, no, we really have to get deep into this, because one mass isn't the same as another mass. Isn't
right.
the same as,
they're talking about two different masses.
You're using the same word, mass, but if you use it,
referring to different things.
So you might as well use two different words.
Yeah. So when they talk about the mass of the top quark being more than or just let's just say equal to the mass of a gold atom, they're not talking about the quantity of matter notion of mass. They're not talking about the same thing when they're referring to atomic mass, which is the number of protons or neutrons inside an atom. Now they're talking about the amount of energy necessary to accelerate or strip quark from its proton. And they need more energy to do that than they need to accelerate a gold atom. So they say, well, it takes about as much energy to accelerate a gold atom as it is to remove a seed, a quark, from a top quark in this case, from its atom, from its proton.
Well, yeah, but it's kind of wrong to talk about how much energy is necessary to do something, because you might be using an inefficient method of doing something, right?
Yeah, it's a linguistic trick.
No, you're not getting me. Uh-huh. If I want to move a car, right?
Yeah.
I can use gas to move it. That's X amount of energy.
Yeah.
Or I could get a whole bunch of people to push the car, which is a different type of energy, which is less efficient. Just because we need more energy to do this than that doesn't mean that the car weighs more all of a sudden.
Right, and they're two different concepts. That's all these people.
And all of a sudden now
hold on, we have a question here from Steve Schrader. Why don't you go ahead and read it out here?
Steve Schrader says, if this arrow gets out of my face, I can't read it.
Well, now I'm really confused about atomic mass and atomic weight and just exactly how they come up with these figures. Even brings up how the number of protons are figured and the number of electrons. Yeah, these are very valid questions, Steve. And it seems the number of neutrons are actually pulled out of there. Yeah, it's if there are no such thing as particles, we have to start even questioning that. But if we concede, let's assume that we concede that there are balls called protons and balls called neutrons, which, at least according to the rope hypothesis, we have no problem with that part of it. The question is, can we go deeper and say that a proton is made of 3 quarks, a neutron is made of 3 quarks? Does that make any sense? What are they talking about at that point? And at that point, yeah, you have to wonder, because keep in mind, the electron is also treated as a little bead that goes around. And when you say, well, is the electron really a little bead? And the answer to that is, well, we don't know where the electron is. Well, that wasn't my question. My question is, are you saying that it's a bead? And you're talking about location.
Yeah, what is the thing we don't know where it is?
Right, and so the issue is that they say, well, all we can talk about is location, because we've never seen an electron bead.
But I think what he's asking, which, I mean, is a valid question, how do they know how many protons gold atom has?
And again, they do these things by weight, and one of those is the mole, the definition of the mole, which is you can come up with a number of atoms that are comprised in a certain weight of whatever element, and they came up with this number, 6 times 10 to the 23rd. Avogadro's number.
What is that?
That's the number of atoms in 1 mole of a substance.
Okay. So we weigh a gold bar.
Weigh so much, we can tell you how many atoms are in that substance.
How do they come up with that?
Through Avogadro's number. That's a long story, but
that's a story for tomorrow.
That's a story for a rainy day. The point is that they come up with these numbers, and they say we can tell you how many atoms are in there, because for every mole of any substance you have only 6 times 10 to the 23rd atoms, I think is the number that they have up there, and that's
you multiply with
weight. And so by weighing something, you can say how many atoms are in there. I can accept how many atoms. That doesn't mean that we can say how many, and we can even go to the level of protons and neutrons. Maybe we can get up to that level. The question is, can you extrapolate that one step further and say, okay, let's talk about quarks and gluons? Well, the gluons are left up in the air. Those are unlimited. You bring them in.
It's kind of like dark matter. Whatever is missing in the equation, we fill with gluons.
You can always invent the number of gluons you want, because you can just introduce and say, well, there's an unlimited number of gluons, so we can pull this out of nowhere. Something like the steady state universe for general relativity. This is something similar, but for the quantum world. That means particles are created from nothing constantly, as you can see also with the creation of quarks from pulling 2 elastic gluons apart, and then the quark forms at the end. Okay, so they're creating matter out of nowhere, and just like they do that, they're simply creating quarks and gluons out of nothing. So you have to start wondering about
what it is we're seeing, what it is
we're interpreting,
and what it is we're calculating.
Yeah, and so again, a lot of this stuff is up in the air, and that's why they always say, look, we don't really know what happens there. These are our explanations, and we don't give a damn about our explanation because that's all philosophy. We just do math equations. With that, we'll see you on Sunday, and maybe we can answer some more questions regarding gluons and quarks. Very fascinating topic.
Yeah,
really.
I think we'd like to know next time, or maybe we can talk about what's his name's number?
Oh, Avogadro's number.
Avogadro's number.
Yeah, there are
That'd
finer points here, and those are interesting to cover at a different session. But anyways, with that, we'll see you on Sunday, and same time, same station. See you then. Bye-bye.